right, everyone, take a seat, please. Take a seat. Hello, you've come just at the right time. Now, you made it. Well done. I was thinking, oh, it's not a very nice day. You know, people are probably wet. But you made it, okay? Well done. So, before we get started, I hope it's all warm and dry where you are at home, okay? Now, before we get started, what's happening next week? There is a major event. Apart from ex-cyclones, there's a major event happening. Lab test 1, right? This is almost as important as a cyclone. Yeah? So, the practice questions are ready. You should do them. You should do the timed version as well. Okay, one of the biggest mistakes that students make is that they can do all the questions, they know what to do, but they don't do it under exam conditions. Okay? All right. Now remember, the questions for lab test 1 are just drawn from the practice questions. Okay? You've got 40 minutes. You need to do your calculations by hand. Not my rule, but that's just the rule. But you get to use, oh gosh, you're so happy to be here. I know, it's great. You can use the how did I do button as much as you like. And people, that's good, right? I think you should be able to do that in first year as well, just my opinion. Now, somebody asked on Moodle, if I use the how did I do button, do I lose marks? The answer is no. Okay, you can use it 20 times. You know, you put in 1, how did I do? Put in 2, how did I do? 3, pi, e, root 2, -1. Something's got to work. All right. So, in today's lecture, we are going to continue with what we did last week. So, last week, we set up the idea and the computation of integration in like 2 dimensions, okay? And one of the motivations for this was what you saw at school. You know, if you want to compute the area here, you basically slice it up. Remember Riemann sums? Oh, they're lots of fun, right? Riemann sums. So basically, you've got a lot of rectangles. You want to compute the area under the curve. You make the rectangles really thin, and in the limit, the area of the rectangles and the area of the region is the same. Okay? It's kind of the same for volume and area with double integrals, except instead of having a one-dimensional base, you've got two-dimensional bases, right? So that'd be like delta x, delta y, and then you've got a little piece of the surface that's above that. Okay? So with this setup, it's the same deal that you know from school. The volume is just the base times the perpendicular height. We can do that using double integrals. Okay. So we showed you how to compute these things. You can do it in an iterative manner. And the easiest case is when you're integrating over rectangles. So here, y is between 2 and 3, x is between 1 and 3. Okay, so if you were drawing a little rectangle or a picture of the region of integration, so 1 and 3, sorry, 2, let's do that. 1 and 3, so there's x, there's y. Oh, sorry, let me do that again. So just from this picture here, so 1 and 3, 2 and 3. That would be like a very simple picture of the region of integration. And you've got a surface above or below that. Okay, so the integration wasn't very difficult, but then it started getting more difficult. Yeah, so this was the example that I finished on. And this thing's still not working properly, which sucks. But this is like a level up from the rectangles. Okay? So with these ones, it's not so nice and squarey or rectangular. It's actually curved in this case. Okay? So one of the key things that I mentioned was to draw a picture whenever you can. Okay? The actual integration itself isn't that difficult. But what is difficult is setting the integral up. Okay, setting it up, and then you can calculate and do all your stuff, right? Okay? So, let me give you a little bit more about these sort of ways of describing the boundary and the set. All right? So, one way is to basically draw a vertical line and a horizontal line. Okay, let me say that again. A vertical line and a horizontal line. So let's just draw one. Okay, that's my vertical line. Now, look at the region. Where does this line enter the region? It enters it at y equals 0. Where does it leave the region? It leaves the region at y equals 1 root 1 minus x squared. Okay? That's probably the easiest way to come up with the sort of the edges or the curves that are involved. Okay? So this is kind of where this vertical line enters the region, and this is where it leaves. So if you're not sure, draw a picture, draw say a vertical line, look for the places where it enters and leaves the region. You can also do it horizontally, right? Okay. Oh, this is good. Can I use how did I do a Google times? You can. If you can type that fast, right? Yeah, you can. Only once though in lab test 2. Only once in lab test 2. Again, not my rule. All right, so today we're going to look at the next level of double integrals. This is called reversing the order of integration. Now, the order of integration doesn't matter if it's like a rectangle or something like that. It's usually pretty easy. But when you've got these non-rectangular regions and you've got something like this, there's a problem. Okay, let's be a bit naive and just try to do it normally. Okay, so just to refresh our memory, you do the inside integral first. Right? Imagine x is a constant. There's no x's in there anyway. But who can tell me what's the problem with doing the inside integral first? What's the problem with it? What is it? What's the antiderivative of square root 1 plus y cubed with respect to y? Hang on, I've got money. I do, I've got money. Go. Yeah, that's all I got. That's all I got. Right. Can somebody find the antiderivative with respect to y? That's not as a series. Not as a series. I'm looking at you people at home too. Okay, can you do it? Let me know. Oh, it's lighting up. Oh, Wolfram Alpha. Right? What's the problem with this? you can't find the antiderivative. You can't find the antiderivative with respect to y. But let's say in a perfect world, in a nice, warm, dry, unflooded world, let's say I could switch those. Okay, so I'm switching the order and I might have to do something here. Isn't it easy to do this? Would you agree? So you imagine all the y's are constant and you integrate with respect to x. So it'll just be x times that square root, whatever. So in the first case, you can't do anything. In the second case, it's super easy. Okay? So this is a trick. You know, like if I was being all professory, I'd say, oh, you don't like it? Oh. It took him 11 minutes to work that out. This is a trick or a strategy, if you want to, be a little bit, strategy, that you can apply to problems like this. Okay? Because, we know that it should give you the same answer because volume and area don't change. So even if we swap the order of integration, it should give us the same answer. Okay? So that's what we're going to talk about today. And I almost guarantee you that you will get a question like this on lab test 2. Almost guarantee. Not a guarantee, but almost. Okay? And so what do you need to do to solve a problem like this? First of all, you need to understand that there's a strategy. You know how to apply the strategy, and you do that by drawing a picture. Okay, and redescribing a two-dimensional region. Okay, so let's have a look. So, better. And this is just sad. Okay. It's non-elementary, exactly. So someone at home has piped up, it's not elementary, it's bands. So basically you could grind that integral out as a series, but you wouldn't call it what we say as an elementary function. Okay, so let's do this. First of all, draw a picture. Okay, so here, our region of integration. Okay, so x is between these two lines, 0 and 1, and y is between 1 and root x. Okay, so I'm going to draw a picture. So let's go with x. So x is going this way, x is between, that's x equals 1, this is x equals 0. Then y is between 1 and root x. So just think of y equals root x. Y equals the square root of x. Okay? So y is less than this horizontal line, and it's bigger than, let's say, that. Okay? Whoop. Okay. Now, let's draw, say, a vertical line. All right? We want that the region where that vertical line enters at y equals root x and leaves at y equals 1. So is it the top or the bottom? The top or the bottom part, which is our region of integration? The top, exactly, right? That doesn't change, right? That's our region of integration, okay? We spend time on this because we're going to have to describe it using y between two horizontal lines and x between two other curves. Okay? All right. So one way you can think about this, instead of having y equals root x, you can have, oh my God, x equals y squared. You just basically write the graph as a function of y, or the curve as a function of y. Okay? All right. So let's see if we can redescribe it. Okay. So instead of drawing this vertical line, let's go horizontal. All right. The green comes into the region when x equals 0, and it leaves at x equals what? Sorry, that's not working. Eh? So let me pose that again. You've got these boundaries, right? So if you're going sort of as x increases, you come into x equals 0, this is the line x equals 0, and you leave at what? Y squared, right, that's it. Okay, and then it's like, okay, well, what horizontal parallel lines are we going to use for y? Well, in that strip, that's where the y is. Okay, so that's my description. Okay, now once I've got that description, I can sort of exhale and I can just write down my integral. Okay, I can just write down my integral now. Okay, so let's do that. So I'm going to use the limits of integration here, and because y is on the outside, I want it to be like that. I want the y to be on the outside. And the thing we're integrating hasn't changed. Okay? So now that's completely changed the accessibility of this problem. Okay? That has completely changed it. So what would we normally do? We'd go, okay, let's do the inside integral first. Okay, I'm integrating with respect to x. There's no x's there. So I can just, yes? Hang on. Everybody at home.
So we can switch it from the bottom being the square root of x and the top being 1 to now 0 to y squared? Mm-hmm. How exactly does that work?
Same region. So instead of using two parallel vertical lines and two other curves to describe our region, we're using two parallel horizontal lines and two curves. We're just redescribing things slightly differently. Okay? If you're unsure, do the just draw in some lines, a vertical line and a horizontal line, and see where it crosses. Okay? It takes a little bit of practice, but drawing a picture is super important. Okay? All right, so let's do the integral. This is just x times that. Super easy. Yep. So I plug x in there, I'm going to get a 0, I'm going to get a y squared. And so now it is a single integral, and we've got to work that out. So what is the key here? You can do it by substitution, but it's even easier than that, right? If you sort of look here and here, the y squared is the derivative, almost, of 1 plus y cubed, right? So what's going to happen to the square root? It's going to become 3 on 2, and you just got to massage it, okay? So it's going to look something like that, and I've just got to maybe put a number out the front to make it work. So that 3y squared is going to come to the front. The 3 on 2 is going to come to the front when you differentiate it. And so you can all right, sub those in. Kaboom. Okay? Yes? Oh, hang on. Let me just check. Oh, yeah. So, yep, you're right. So we've done the dy. Hang on. That should be a dy. Exactly. Thank you. That's it, right? Thank you. Good spotting. All right. So the difficulty there, I mean, there's some difficulty doing the integration, but the main thing we want to test here, and the main thing you should aim for, is setting it up where the order is reversed. The order of it. So instead of going dy dx up the top, you're going dx dy, because you can't do it any other way. I mean, at least you can't do it as it stands, because there's no antiderivative of root 1 plus y cubed.
Sorry, but where did you get the 2 over 9 from?
Okay, so I realized, I think I did, that this, right, this is the derivative of that. Would you agree? Or almost, right, up to like a factor of 3. Yep? Okay. So I'm thinking, okay, well, this power of 1/2 is going to increase to 3 on 2, right? And then when I differentiate this, I want to get that. So that 3 on 2 is going to come to the front. That 3y squared is going to come to the front. I'm going to have 9 on 2 as a number. Okay? So I want to combat that by multiplying by 2 on 9. Yeah? Now, the long way here would be doing it using a substitution. You can integrate by substitution if you're worried. Okay? But obviously, you've only got so much time in the test, and, you know, but it's up to you. Yeah. Other questions? What's happening at home? I've still got my $50 for now. What's happening? No, not a lot. Okay. Questions? I almost guarantee you'll get a question like this. Not a guarantee, but almost a guarantee. Okay? I almost guarantee you. And where do students fall over? Where do students fall over? They can't draw a picture, right? They can't describe a two-dimensional region, and they can't redescribe a two-dimensional region. The actual integration isn't too hard, right? That's the least of your worries, okay? But as engineering students, I would hope that you can, you have some visual capabilities, right? I would hope. I mean, it's probably not so important now, but it's just a good way to think if you can do it. Other questions? It's a super, super, super important one. Okay? Yep. Hang on. You're speaking to the mic. So
Could you please re-explain why 0 is lesser than equals to y is lesser than equals to 1? And also this part.
Yeah, so instead of, so usually when we set these double integrals up, there's constants on the outside. Okay, otherwise it's not going to give you a number. Okay? So it's like, you'd call this a definite double integral because you want a number at the answer, right? So in here, x is between 0 and 1. In two-dimensional space, they are vertical parallel lines, right? Would you agree? Yeah? Yeah, so you get that bit. So what bit don't you get? Well, so instead of using 2 parallel vertical lines, we use 2 parallel horizontal lines. Okay? And so y is trapped in that strip. It can't, like, if we restrict y to that strip and we smash it With the other part, where the x is between 0 and y squared, you get that shaded region. It's the intersection of two sets. Yeah? It's a good question. Okay, super, super, super important. Let's do another one. Let's do another one. On the stairs. All right. This is another classic one. Okay? So the 50 bucks is coming out again. It's coming out. Oh, where's it go? Oh. Let's do it. Okay. All right, it's coming out. I thought someone had like taken my 50. Now, is everything all right? You guys are like in fine form, hey? Okay, good. I'm glad. Okay. Okay, so question. What is the antiderivative of sine of y squared with respect to y? Please tell me. Sounds pretty easy. Oh, it's like negative cos of y squared all over like 2y. No. It's a good try, but no. Why isn't it like anything to do with cosine? Because if you differentiate it, you don't get that. Okay? People have walked down in previous classes and they've gone to take my money. They're like, oh, it's cosine of y squared all over 2y with a negative. Give me my money. And then I have to say to them, oh, can you differentiate your answer? And they're like, yes. And they don't get what they want. Sorry. Okay, so they even told you in this question, reverse the order of integration. And who checked these notes? Evaluate. Okay, so money's just going over here for a minute. All right, so instead of doing the full integral, let's just set it up. Because sometimes you're just asked to set up the integral. You don't actually want to evaluate it. This is very common in some maths courses. Okay, so what do? Let's draw a picture. So here, our region of integration. Okay, x is between 0 and 4. So they're two vertical lines, parallel. Y is between 12 and 3x. Okay? It's a very good question online. I will get to that in a minute. Okay, so let's draw a picture and see how we go. So okay, so let's draw in the line x equals 4. Yep. Let's draw, well, x equals 0 is just the y-axis. Y equals 3x and y equals 12. Okay, so let's just go up here. We'll imagine that there's, different scaling on the axes. Okay? And so now we want to work out, it's going to be one of the triangles, yeah? Stupid thing. So which one is it? Okay, let's grab pink and 0x4. Okay, so the 0x4 is that whole strip there. Okay, it's like infinite strip, right? Let's go with y is bigger than 3x, so we're going to, blue. So we're going to draw a vertical line. We want it to enter at 3x, which is there, and we want it to exit at 12, which is there. So is it the top triangle or the bottom triangle that we want? The top, right? The top. So that's our region. It's a triangle, right? It's a filled triangle. That's the region of integration. Okay? So let's reverse, let's redescribe it, and we can set up the integral. So instead of having y as a function of x, let's do something dangerous and have x as a function of y. I know. Crazy, huh? Okay? And instead of having two vertical parallel lines, let's have two horizontal parallel lines. Okay? So, let's try that. So, who can tell me what our two horizontal parallel lines are going to be for the boundary for y? 0 and 12. Exactly. Okay? 100%. So now we've got this infinite strip. Okay? Now, brown. Let's draw a horizontal line. We enter here, we leave here. So what will the bounds on the x be? Yeah, it comes in at 0, spits out at x equals y on tree. That's it. It's the same region, it's the same function that we're integrating. We've just described the region equivalently, but using a slightly different way. Okay, so what will our integral look like? We're going to swap the order. We're going to use these things now. So the y is going to go on the outside. The inside integral is going to be this. And that. And hallelujah. We can now integrate sine of y squared with respect to x, which is easy. Okay? Which is easy. Okay? Question? Okay. That's fine. So, you integrate it, you're going to get x sine of y squared. Do something with that and then integrate it again. Questions? Let's have a look at home. All right, people are getting a bit crazy in the chat now. This is good. All right. Second thing, is it possible to evaluate a double integral by reversing the order of integration but without redefining the region? Yes, if it's a rectangle. So if the region is a rectangle, it's fine. It's all constants, right? That's fine. But here's a little secret. I shouldn't be telling you this, but I will. You can actually use integration by parts to solve some of these problems. Okay? And I worked that out about 10 years ago. And I wrote a little research paper about it. I can't believe it. I'm actually speaking about it today. It's like the highlight of my year. So if you want a copy of that, I'm happy to send it to you. Right? I'm happy to send it to you. Or I can post it on Moodle or whatever. But this is what they want you to do. And if you look at the Mobius questions, they really want you to do this, redefine the region, what are the boundary functions, whatever, and then what's the answer, okay? So you can do this using integration by parts. In fact, I haven't found an example where you can't use integration by parts yet. But yeah, it's not great. Okay. Oh, did something just disappear from that chat? Yeah, something just disappeared. All right. Questions? Questions. The way to get good at these problems is to do as many as you can. Okay? Draw a picture. Think about the boundary.
Just a stupid question, but like, could you describe the boundary without drawing like the graph? Could you just do it manually? No way.
No, if it's a rectangle, it's pretty easy because you just got numbers, right? X equals 2, x equals 4, y equals 1, y equals 6 or whatever. But when you got sort of curves and it's not great. So yeah.
Could you please re-explain which side of the triangle we know to like refer to?
Okay, so let's have a quick refresher in 2 dimensions. Okay? So let me just draw another picture. Okay. Let's say this is the line y equal x, and that's 1 and that's 1. Okay? All right, so let me draw the region first, and then you can work it out how we should describe it, because maybe that's even easier. Okay, I'm going to go with this region. Okay? I'm going to go with that region. So if I'm using, say, my y, remember, y is sort of the vertical direction or the vertical axis. It lies above this and below this. Yeah? So it's trapped. Would you agree? Okay? So all we need now is 2 horizontal lines. We're working vertically there. 2 horizontal lines that are parallel. Right? Oh, no, sorry. What am I saying? We're going that way. Gosh, even I'm getting confused. All right, so we want to go that way now. Okay? But we want those 2 lines there. So that's x equals 1, that's x equals 0. So x is between 1 and 0. Okay? So you can re-describe this. You can flip it around. You should be able to do that instead of using, you know, put y between two parallel lines and x between 2 other lines. Okay? But this is super, super, super important. Super important. You know, this is one of the questions that you see in a course like this. Can you bring some geometric or some visualized understanding to a problem like this to solve the problem? Okay? Questions? Okay. All right, so we've already talked a little bit about integrals and area. This is another kind of question that you might have actually seen at high school. And we're going to look at it through the lens of double integrals or integrals in higher dimensions. Okay? So let me just draw a little picture and I'll show you what I mean. Yeah. All right. So let's say I've got a region like that. Okay? I'm just sort of freehand drawing it. And I want to work out the area that's in that shape. And at school you go, okay, well, if I know the top function and the bottom function, I can just look at the difference in the area under the curves, right? But with double integrals, what we're doing, we're actually slicing this up in 2 ways. So I want to calculate the area of that. What I do, slice that way and dice that way. Okay? So when I first showed you this thing at the start, we were only slicing in sort of along one axis. We were chopping up the x-axis, if you like, or vertically. Here, oh my goodness, we're going vertically and horizontally. Right? It's like an infomercial. Vertically and horizontally. Yeah? So what are we left with? We're left with a lot of rectangles. Okay? And so if I compute the area of each of these little rectangles and add them all up, I'll get an approximation to the area of the shape. Would you agree? Okay, all right. So let's talk about the area of a little rectangle. And the sides are going to be delta x and delta y. Okay? So there's sort of the width of our cuts. So what will we do if we want to like approximate the area? Just sum up all the areas of each little rectangle. Yeah? So what will happen is right? Okay? And then in the limit, that's what we sort of represent this simple double integral by. If you want to sort of give it a little bit more meaning for what you've already learned, you can say, oh, the function here is just the constant function 1. Okay? So in the limit, your little rectangles get really small, you add them all up, and whatever value you get, assuming it exists, is the area of that weird shape. Okay? Great. That's Riemann sums again, right? Remember Riemann sums from 1131? They were just awful. Does anyone really remember Riemann sums? No? Yeah. Let's not go back there. Yes, you do? Yeah, it is. It's a 1. It's a 1. It's a 1. Sometimes, yeah, if you can't understand it, just, I mean, I do that. People do it all the time on YouTube. They're like, your Zs, they look like 3s. I'm like, that's just the way I write. So, yeah, I get it. Wow. Okay, so what about this one? You can do this using high school maths, but let's see how we can do it using double integrals. Okay? Let's see. All right, so, So, using double integrals, calculate the area of the region bounded by these curves. All right, so I'm just going to draw in the curves. I've got x onto x and root x. Okay, so let's say that's going to be x. This one might be root 2x, and let's say that's root x. Okay, so this will be y equals x on 2, and this one will be y equals root x. Okay, and so you look at it, you've got a point of intersection there, and you really want that area. Okay? So, we've sort of got two regions here. Let's call that, I don't know, omega 1 and that omega 2. Okay? So, these two graphs are going to intersect at x equals 1. These two graphs are going to intersect at x equals... Just hang on a sec. Yeah. Yep, that's right. Yep. So it's that and that one. Okay. So the way I'm going to do it with our double integrals is I'm going to calculate the area of omega 1, the first bit, which is pretty easy. It's like a wedge. And then the area of omega 2. So let's just set it up, and we may or may not evaluate it. Okay, so this is what we're going to use, and we're going to have our limits of integration in there. So let's see how it works. So let's do omega 1. All right, omega 1, you can say, okay, x is between 0 and 1. Right, and y is going to be bigger than this curve but less than this curve. Let me say that again. X is going to be between 0 and 1, and y is going to be above this curve but below that curve. Okay? So let's do that. So y is going to be bigger than x on 2 and less than x. Great. So let's think about lambda, omega 2. All right, so here x is between 1 and 4, and y is going to be bigger than this curve, but less than that curve. Oh, no, yeah, exactly, and that's root x. Okay? So we have to do two things there to describe the little bits, the little regions that we're integrating over. Okay, so let's just compute the area. So area, okay, let's set these things up. Let's go over lambda 1, omega 1 first. So 1 to 0, x on 2 to x, think of it as 1. 1 to 4, root x to x onto dA. Now, this will be, I've written out dA here, but let me adjust that. This will be dy dx, and this will be dy dx. Okay? dA is sort of like a placeholder for dx dy or dy dx. Okay? But once you've put in the limits of integration in the integral signs, you need to specify the order. Okay? So we integrate those. And what do you notice? It's the exact same thing that you had at high school. Okay, the area between two curves. So double integrals gives you a connection to stuff that you already know, basically. Okay? It's area, so square units. So there you go. Not a hard problem, but an interesting connection with stuff you already know. Double integrals and integrals between curves are kind of the same thing. You just didn't know it at school. Okay? You just didn't know it at school. Questions? Excellent. Yeah. Your integration song on SoundCloud pops. Thank you. I do try. I try to be as daggy as possible. Yeah. But if you like it, I'll play it. Actually, maybe I'll play it in the break. Questions? Questions? Yes.
Could you explain why the area is 1 again, or use the double integral one?
Like, because the only reason I'm putting that 1 in is because we've been integrating functions, right? And so if you leave it, if you had just this, some people, they freak out. They're like, but where's the function, bro? Where is it? What does that even mean? I'm trying to say, well, think of the function being just identically equal to 1. Okay? But you can ignore it if you want to. Yeah. Other questions? Okay, let's take a break. 10 minutes. Stay dry, we'll be back. All right, let's get back to it. We're almost at the end of the day. Does anybody have classes after this one? Does anyone have classes after this one? Okay. Yeah. I always feel sorry for the students who come in afterwards. I'm like 6 to 8. It's like a long, Don't worry. Back in the day when I was at uni, I would have one day, it was a Tuesday. The lectures started at 8 a.m. and they finished at 9 p.m. That was just the worst day ever, hey. Yeah. Anyway, I appreciate you hanging around. So, let's look at the connection between double integrals and area and we summarize what's going on and we see the bigger picture. All right. So let's have a look. We can think of this double integral representing the area of a 2D region, okay? Now, some people were talking about, hey, how does this connect with volume? How does this connect with volume? And I'm glad they asked. Okay. Imagine you've got the plane, horizontal plane, z equals 1. So it's parallel to the xy plane, and it's, right? And you have the base is your omega shape. Okay? The base of whatever volume we want to compute is like a 2D omega shape, whatever. The volume above the omega region and below z equals 1 is a volume, right? It's the same as the area of omega. Okay? It's the same as the area of omega. So whether you want to come at it from a volume perspective or an area perspective, they're both correct. Okay, they're both correct. People are going, oh my God, it's the same volume and the area. Okay, let's look at another example. Okay, double integrals to compute the area. Now this is really a high school problem, but let's just set it up and see what happens. Okay? So you guys can help me here. It's bounded, so they're the, like, basically, when we say bounded, it means like the edges of those bits, those functions. Okay? All right. So what do? Draw a picture. Okay? All right, so x cubed going to look something like that. And x squared going to look something like that. Okay, this is the worst picture ever. All right. So what bit are we talking about? Well, there. Okay, so the top curve hang on. I think let me just redraw that a bit. Got them in the wrong spot. Yeah, that's better. Okay, so we'll do y equals x cubed for that one, and y equals x squared for that one. So the x cubed curve is lying below the x squared curve. Okay, so that one's your x squared, that one's your x cubed. Okay, and that's 1 and that's 1. All right, so this is obviously, difference of two areas, whatever, high school maths. But let's actually think about how we set up the region. Okay? So I'm going to go with a vertical line. And I want to see as we go from the bottom to the top, where do we enter our region and where do we leave our region? Okay, what are our functions going to be? What's y going to be between? It's going to be bigger than x cubed and it's going to be less than x squared. Exactly. Okay, I can tell you're getting it. Oh, sorry. And x, okay, well x is just going sort of in this strip here. That's it. Okay? Yes? Oh, we'll be pretty kind. Yeah. So for everyone at home, you're not going to get something like, x times the sine of root x or something. It's going to be something friendly like root x squared, x cubed. Yeah. 2x. Yeah. Yeah. Yep. Find out whether, when you draw a picture, you want to find the points of intersection. Yeah, if you can. It's a good question. Other questions? So what would the integral look like? I'm glad you asked. Okay, so y is between that, so dy dx. Bump, bump, bump. Okay. So if you do one step, you see, getting flashbacks to school maths. Wow. Okay. So, yeah, sort of come full circle back to high school maths now. Questions? What's happening online? Yeah, good. If you have any suggestions for math songs, let me know. I haven't had one in a while. I'm sort of running low on ideas. I have 2 kids. My daughter suggested a couple of songs, and I'm like, yeah, I'm not scared to take your idea and run with it. So if you have any ideas, let me know. Huh? What? No, come on, tell me. No, come on, what? It might be a good idea. Tell me later. Okay. All right. Now you can prove things that you already know using these things, right? So we're talking about polar coordinates here. You saw them in 1231, I think, or 1131. You can also integrate with different coordinate systems. So let's look at that because this is also a very important part. All right, here we go. Now, remember polar coordinates. Okay, so instead of horizontal and vertical, what have we got with polars? We've got distance and angle. Okay, distance and angle. So instead of x and y, we've got r und theta. All right, and so you can still do it in the xy plane, but let's say there's your point P. You've got a certain distance to the origin and you've got a certain angle to the positive or x-axis. And as theta increases, you rotate anti-clockwise or counterclockwise. Okay? So that's basically the idea with polar coordinates. And remember, x equals r cosine theta, y equals r sine theta, which is stuff you already know from first year. But what else can we do? Well, for double integrals, believe it or not, the area element, which is dA, so dx dy or dy dx, that in polars changes a bit. It's this form, r d theta. R d theta. Okay? Okay, it's not quite clear why that is, right? So dA in sort of x and y coordinates is either, dx dy or dy dx, yeah? In polars, it changes. And it's not clear why it changes. Why shouldn't it just be dr d theta or d theta dr? That's a good question. Oh. Yeah, r dr d theta.
I was thinking that it's how you find the area of a circle. So then it would be like, it would change into, like the, like a portion of a circle, not the entire.
Yeah, like a sector? Yeah. Okay, so let's draw a picture. Okay. So you've got, in this case, let's say I've got a, I don't know, some sort of curvy thing, right? Who knows? And this is like, that's going to be that, and then you've got some r in there that kind of averages the distance or the difference of the two wodges. You've got a big wodge and a little wodge, right? That's in a nutshell, that's where it comes from, okay? So let's do a problem and work through it, okay? All right. Consider the double integral given by this mess. Sketch the region of integration, so draw a picture. Evaluate the double integral by applying polar coordinates. So the most important things here are drawing a picture, of course, and those representations. Okay? Those representations. So let's draw a picture and see how we go. So y between 0 and, let's call that I, y between 0 and 1 on root 2, and we're in xy coordinates here. And x is between y and that square root. Okay, it's getting a bit funky now. So let's draw a picture. Okay, our goal here along the way is to describe whatever this region of integration is just using polar coordinates, r and theta. Okay, that's sort of the goal. And you'll see how it massively simplifies things. You could probably do this. You could probably do the inside integral first, and then do the outside integral. Nobody's got time for that. Let's be honest. Okay, no one's got time for that. But let me show you what happens when you change the coordinates. It's pretty nice, I've got to say. Okay, so picture. I'm going to draw in all the sort of edge functions. So y is between 0 and 1 on root 2. Let's say that's 1 on root 2. Okay, and there's the other one. And then x is between y. That's x equals x equals y, right? And this thing here, now that is part of a circle, right? Okay? So that's going to be x equals root 1 minus y squared. So now we just need to work out where our bit is. We're in this strip here, and x is going between there and there. So what we want is that bit there. Okay? Yes? Because x is... But that doesn't include the y, does it? Because you're stuck in that horizontal strip. Yeah. Can you see how? Like it's so simple, but like it is hard to put together. Don't worry. Like, and once you're in the zone, you'll be like, oh, you've like made it. No, it can't. It can't go below the x-axis, right? Because that horizontal strip isn't there. No, no. Okay, so how can we describe that in terms of r and theta? That bit there. Can anyone guess? Math 1131. Yes.
R would be between 0 and 1, and theta would be between 0 and pi on 4.
Exactly. So let's deconstruct that a bit. So remember, r is just the length to the origin, right? So this is basically part of a circle with radius 1. So I would do that. And then theta is how much turn you do in the anti-clockwise direction. So I'm sort of doing a bit, sort of quarter of an eighth of a turn. Okay, it's not a good drawing, but so there are your functions or your values of interest. Notice how they're all constant. They're all constant. So you've gone from this crazy thing with square roots and y's and that to like 0, 1, 0 pi on 4. That's a good thing. That's got to be a good thing, right? It's a good thing. Yeah. It is, because we've simplified it. Even on, a Tuesday afternoon when it's raining. I think it is. I'm just going to check the aircon. I'm getting a bit hot. Okay, back on. All right, so let's do it. Let's rewrite this integral in terms of these things. Now, instead of this dx dy, I'm going to have r dr d theta. Okay? That implies that the theta is going to be the first integral sign that I'm going to look at. Okay? So let's look at it. Theta is between 0 and pi on 4. And r is between 0 and 1. And what about this thing? 3 times y is just going to be 3r sine theta. Boom. Okay? So that now, you could argue that the integrands become more complicated. Yeah, I get that. But the constants, the integration symbols, 0, pi, 0, 1, super easy to manage. Okay? Now, let me show you a secret shortcut that some people don't want you to know about. Right? When you're integrating over a rectangle and you've got the product of functions, so in this case r's and thetas, right? They're just products. Can anyone think of a shortcut to do this problem? What happens if I wrote it like this? I'll put the 3 over there. Okay, so I've got one single integral multiplied by another single integral. If you can do that, you should do it. You look upset. How is it? What are you confused about it? If I have something like this, right? Let's say I have they're just numbers, yeah? And I have Yeah? So you've got a function of one variable and multiply by a function of the other variable. Yeah? Okay, and I'm integrating with respect to r on the first one. Okay? Let's just draw in the brackets and see what happens. Does that affect the integral with respect to r? Right? It can't. How does it affect it? It doesn't depend on r at all. So what you can actually do, you can move things around. You can move things around, right? Does that make a bit more sense? Does it make a bit more sense or not? Okay? I do this all the time. Yeah? Is there a name for the rule? Suggestions? What? What's your name? What is it? What's your name? Benson. Okay. We're going to call it the B theorem. All right? In your honor, Benson. Okay? It's now official. Right? B theorem. Okay? Now this only works with rectangles. Okay? You can't do it all the time, but it only works with rectangles because rectangles are super simple integrals. You can turn them into products if the integrand is nice. Okay? So, okay, let's do the integral and see if it works out. Okay, so the first one's going to give you 1. The second one's going to give you something like -1 on root 2 plus 1. Okay? If you don't like the B theorem, you can do it the old way that I showed you last week. Okay, you do the inside integral, then you do the outside integral. No problem, you can do it. But I think it's actually simpler just to multiply two integrals together. Okay? It's up to you. You won't get into trouble. I don't think you'll get into trouble. What do people think at home of the B theorem? I think it's pretty cool. Oh my God. Okay, I might have missed something. What do you mean by rectangles? The two-dimensional region that we're integrating over. Okay? Yeah. Tisdell's razor. I love it. I know. Was this forbidden knowledge before now? Yes, I think it was. Could you explain how I got the pi on 4? Yeah. So let's go back. Okay, it's not a good drawing. Okay, it's not a good drawing. But you know, if you're here, and that's 1, and the height is 1 on root 2, that angle's got to be pi on 4. Okay? I mean, usually I just draw the picture and I work it out from the picture. Okay? And usually the angles are pretty straightforward in this course. You're not going to get anything really difficult. Okay? Hopefully that's a bit more helpful. Okay. More questions? We're going deep into the double integrals now. Now you know the Cartesian form, the x and the y's, right? And you also know polar coordinates. The only thing that's different is the so-called area element. Okay, so what's the biggest mistake that students make? Well, I'm glad you asked. They forget about this. They forget about it. Okay? Don't forget about it. Okay? Don't forget about it.
How did you know the upper limit is pi over 4 for theta?
So one way of doing it, there's a little triangle here, okay? And so the hypotenuse is 1. That's 1 on root 2 because it comes from that, basically that there. That's got to be 1 on root 2. That's got to be pi on 4. Okay, so trig can help you when you're not sure. Okay, but I probably should have drawn a better picture there because it doesn't look like it's sort of an eighth of a turn, right? There. Other questions? Other questions? Oh, this is great. Do polar bears know that we're integrating their region? And I don't know where polar comes from. Does anybody know where the term polar in polar coordinates come from? I don't know. Tell me if you know. I'd like to know. All right. So that's a sort of a standard entry one. What about... Okay, well, let's just go through the bigger picture. These are the most important things. Okay, now you won't get those in the exam as far as I know. So you've got to remember them some way. You know, I'm just in my brain, right? RD theta. RD theta. That's it. Okay? Okay, let's describe the region of integration for this one. Yeah? So that we won't do the integral, but let's just set it up. Okay? Describe in polar coordinates the set of points of the unit disk that has center 0, 0 and line the first quadrant. Okay, this is pretty easy. Assuming you can understand the language. Okay, what are our limits of integration for r und theta? Yeah, r is going to be between 0 and 1. Now, sort of building on what I said before about the lines, if you're not sure about the r, start at the origin and just draw a line through the region. It enters at r equals 0 and it leaves at r equals 1. And what about theta? Or theta? What would the bounds on theta be? 0 on pi on 2, exactly. It's a quarter of a revolution. Okay, so let's write this down in terms of polars. Okay, so we've got a mess, but what do we know about cos squared plus sine squared? Kaboom. That's going to become r squared d theta. That's it. Okay. That's it. So that's an easy integral to do. That's not the hard part. The hard part is setting it up. Okay? The hard part is setting it up. Okay. Questions? Now, what happens if we had a section like this? What happens if we had a section like this? How would we describe that region in polars? Who can tell me? Who can tell me?
It'd just be i's between 1 and 4 rather than 0 and 4.
And theta.
R between 0 and pi on 2.
Yeah, exactly. Exactly. So now we've got a region that is a little bit more complicated, but not much. Yeah? Again, if you're worried about the R's, just go there and just go draw some lines that go through it, emanating from the origin. Okay, it enters at R equals 1, it leaves at R equals 4. Okay? So if you're worried, just draw a picture, draw some lines. Okay. All right, I know it's late. I'm going to do a couple of lab test 2 questions. Okay. Now on Friday, we'll do some revision for lab test 1. But let me show you what you might get in lab test 2. Okay, I've just taken this from last year's. Okay. If you get this one, you should be happy because it's like, yes, this is so easy. Okay? But they do get a little bit more complicated. Okay? They do get a little bit more complicated. So if I was doing this one, I could do something like that and just do the integration. Okay? Now the next one's going to be harder. All right, so I'm going somewhere with this, don't worry. So I'm integrating with respect to y on the first one. Yep. And so now you put in 0 and 1, and you'll get an expression involving x, which is pretty easy. Let's hope. So y equals 0 is not going to do anything. Okay, hello high school maths. Do the single integral. Okay. Something like that. Okay, if you get that one in your class test 2, you'd be pretty thrilled. Yeah. And you can simplify it or not, depending on what you want to put into Mobius. But let's make it a little bit more difficult. Let's make it a little bit more challenging. All right, here it comes. In this question, the next one, this is more difficult. We find the area inside this curve. Like that. Okay, so now this is a little bit more difficult. than what we've seen so far. And look at what the question's asking you. What you've actually got to provide them with? Well, you've got to provide them with the inequalities for the r and the theta variable. Okay? So this is, I would say this is not an easy question. It's certainly not a disk or a quarter of a disk or a piece of a donut or something, right? It's more difficult than that. Okay? But they give you a little bit of information. They say the curve is here. So it's like a four-leafed flower. Isn't that nice? Okay? And we want to find the area. So we basically want to find the area inside the curve. Okay? So the curve is okay. So what will the limits of integration be, say, for theta, for the angle? Oh, hello. Oh, you're in the next section. You come early? Yeah. So I'll make a deal with you. Don't talk. Pretend you're paying attention. Is it okay? You're welcome. Huan Yi. Sit down. Okay. And no headphones. Okay, so the angle. This is the easiest part of the question. What is the theta range between? 0 and 2 pi, right? You do one revolution, you get the whole region. So if I was doing this question, I would do that bit first. Okay. What about the R inequality? Hang on. This is going to be good. I want everyone at home to hear this. No pressure.
The graph touches the circle at pi equals pi on 8. So then we just substitute that into our equation to find what the max radius is. And so the radius will be between not 0, it'll be whatever the smallest value is. Oh no, it'll be from 0 to whatever that value is.
Yeah, sorry. Hang on. You hang on to the mic. Okay, so let's go back to to the method that I showed you before. If you're not sure, start at the origin. Start at the origin and draw some lines emanating. Yeah? So where does it enter the region at 0? Where does it leave? It leaves through the curve. So I would say, oh, you early as well? No. What? Are you in this class? No. What class have you got? Next one. Yeah, what's it called? You can. So thank you for joining us. So we start at 0, and then we leave whenever we touch the curve. Yeah? So what would our thing be up here? 4 plus 2. Bam. Okay? It's a crazy curve, but it's what we want. It's what we want. You don't want the exact value because it changes. So yeah, so it won't be a constant, and you don't want to maximize it here, because otherwise it would be a disk. Yeah, otherwise it would be a disk. So let's set up the integral and see what happens. Let's set up the integral and see what happens. Okay. So, yeah. So actually, here's one I've done earlier. Now, I'm just putting this up just to show you quickly. The first integration's okay, right? So this integration's fine. But then you get down to something annoying like that. Okay? You get down to something involving the integral of sine squared. And it's like, oh, come on, math 1, 2, 3, 1. Math 1, 2, 3, 1. I thought I could forget everything. But let me show you how you can compute that integral without calculus. Okay? Let me show you how you can compute it without calculus. Would you agree that sine squared plus cos squared equals 1? And so if I integrate everything there, say I want to do that integral, it's from 0 to 2 pi, the answer is going to be 2 pi. Now, these two integrals are the same. So what does it mean? It means 2 times this integral is 2 pi. So that sine squared integral is just pi. That's how you can do things like integral of cos squared, integral of sine squared, without calculus. And I love calculus, but we haven't got time for that on a Tuesday afternoon, right? That is amazing. Even if I say so myself, that is amazing, right? Cos squared plus sine squared equals 1. You can use that to integrate all sorts of stuff. It's freaking brilliant. Okay? So this is an easy integration. This is an easy integration. This is not, but it is if you know that. Okay? Everything okay? Yeah? Okay. It's been a long day. Come down for some consultation if you have questions. If not, have a great evening. Stay dry. And maybe I'll see you tomorrow. Okay?